So yesterday, I claimed that if I apply this change factor V to this in the component of the projective object, you get the same thing, taking the hypercohomology, intersection cohomology complex of the closure of the Brunner side. So this is the FC. And the C was the homology ring of the factority. Okay, perfect. Or if you prefer, it's the metric algebra of H modulo the idea generated by the invariance of positive figure. And today I want to explain a bit why such thing should be true. Okay. And okay, I mean, as usual, there is work to do, but I think I cannot talk about category O without talking a little bit about translation factors, and because they are linked here, let me explain a bit about translation. So what is this? I will now just use for to simplify matter object of category O will have only integral weights. Okay, so this is the object of O such that if a weight space is non-zero, then the corresponding weight is integral. And this has the advantage that it will decompose now along the center to add to all these blocks, say, pi. But I sort of would rename them, just rename them, and say it's the block O lambda. Lambda runs over the dominant integral weights, but I put a minus row up front. This. And then these O lambdas here are just the same as the O psi lambda before. So part killed by part of the center. Yeah. So this is a sort of more simple situation. And now if I have two of these blocks, so if I have lambda and mu, which are dominant integral weights, well, up to a shift by minus rho, then I define a factor from lambda to mu. First starts with the category of lambda, goes to the category of mu. And this T means translation, so this is a Janssen and Janssen, I prefer Janssen's translation factor, but Zuckerman, there's also Zuckerman, there's very similar things. Translation. functors. And I don't know, Jan Janssen was a young postdoc, sort of, and Zuckerman was also a young postdoc, sort of, whatever. Yeah. And so what is this translation? Well, this is quite simple ideas, namely, you take E, finite dimensional representation, so simple, simple, and extremal weight, so finite dimensional, and the extremal weights the Weilbrook orbit, I mean, and the weight of the finite dimensional representation would always be stable under the Weilbrook. And if we fix the extremal weight to be the difference of lambda and mu, now this is an orbit, and we take these extreme weights. And this is an E, and then we consider the factor if we have some object n, so this is NO lambda. Then we map it to, well, we tensor with E, and then we project onto the new central current. We take the pulse with the correct new central current. And this will be then in O. And this is the transition I've got. And this is just the principle of the complex numbers. And so I could write it. So I could write it as, okay, that I take the inclusion factor to O, yeah, which would be, say, the inclusion for lambda. And then I apply this tensor factor. And because the finite dimensional representation always the can't extend simply, so it will stabilize the function O. And then I take the projection factor down to O U. This. And okay, and then there are several things to check for this factor. Standard properties. I mean, the most important is why I could just take an arbitrary finite dimensional representation and do the trick. But if I just take the extremal weight, then I can sort of better control the objects. Let me make a little list of what this functor can do. And this is maybe the most important thing. So this is the factor P lambda mu. And the first thing I claim is that if the isotropic group of mu, with respect to the dot function, yeah, so this contains the isotropic group of lambda with respect to the dot action. Then if I translate the Lerma module, lambda x dot lambda, get again the Lerma module. Well, this is sort of the most important property. So So let me try to explain why this is true.
What is X?
X is any element of the triad. So let me try to explain why this is true, and then make a picture. Yeah, I have. Here I make a picture of SL3. Here this point is minus rho, and these lines are not the roots, but they are the reflecting line. And here is a reflection S dot reflected on this wall, and the other reflection dot reflects on the other wall, and here may be zero, and here is sort of 6 plus, yeah. Well, only integral weights, yeah. So this would be the highest weights of finite dimensional percentage. Yeah, it looks like this. Okay, and this is a simple reflection, but sort of shifted, so that they fix minus rho. And now I take some take it away again, and I take some lambda in here, say here, this would be lambda, and then I mean the simple of this category will be just the Lx dot lambda x translated by group. So the simples will have highest weights here, here, and here. So here this will be the simple object of this whole. And now I take a mu, for example, y not here. Okay? So at this point, this will be mu. So this will only have 3 symbols, right? This and this. This is the orbit of the mu. The isotropy group of the mu is bigger than the isotropy stellar. And now I take a finite dimensional representation, which has this extremal weight here. Yeah, let me. So the extremal weight of E should be this difference here. Well, this is mu. Maybe so the E would be mu. Well, L, this mu is not dominant. I mean, I should rotate it so that dominant. I can maybe L minus mu. Maybe not a good notation. But let me draw the weights of E roughly as a circle around here. Yeah. So the weights of E, if I add them to lambda, they will form such a set. So what I have drawn here, this here is say weights of E. But right, this is roughly this set here, and now there is an important thing, which is called tensor identity. which tells us that, well, okay. And this is the quite fundamental thing. Um, so imagine if you have two algebras, for simplicity, let one be in another. So this is two algebras. And E is a representation of G. And then and I have a representation of B as well. Say D is a representation of B. And then whether I first induce up my representation of C and then tensor with the C. This will be isomorphic to first tensoring C with a restriction with a knife. So I tensor with a restriction of E, so it's restricted from G to B. And then this whole thing is induced up. This is isomorphic representations. And why is this? Well, this is what it's called tensor identity. And this is because all these are adjoint factors of something easy. Namely, if we take G modules and we tensor a G module, no, we don't tensor. We make a Hom from E to something. You get another G module, and then you restrict scalars, you get a G module. So this is the Hom C, which is it. Or if we first restrict scalars, the E modules, and then form this homomorphism of representation of the restricted representation to something. This is just the same thing. Right? First taking the, I mean, if there's two representations, you can form the Hom state. This is again representation. And if with this representation, this construction, we then forget scalars, or we forget first scalars and make this construction, it's clearly the same thing. So if we take adjoint factors, it has to give you the same thing as well. And this is what is written here. The first sort of issues and then tensor with E. Tensoring is adjoint to this Hom thing, yeah. Or the other way around, it's just same case. Okay. So this is its tensor identity. I should draw it. And this tells us that if we now apply it to a Werner module, yeah, so we take our semi-simple algebra, and then here we have the Werner. No, we have here E tensor C lambda induced up. Or we first take the Werner module and tensor is just finite dimensional representation. And this is the same thing. Yeah, this is what is written here. And so this means, and we know that this guy has a has a flag with one-dimensional subquotients, and we know the subquotients. And the Borel is a solvable here, solvable here. So we get that this thing has a Werner flag with subquotients, quotients delta, say mu plus lambda, where mu is in the set of weights of phi. I just write phi like fois with multiplicities. Yeah, so it's a set with multiplicities. Because every weight space has a dimension, I take this as a multiplicity. So this guy has a Werner flag with these subquotients here. So this tensor product here has a filtration, a Werner flag, where the subquotients have highest weight all around here. Yeah. But now I look at the central characters of these guys and see and because I project to this central character here. So all the wrong Werner subquotients die from projecting to the correct central character, and only this one survives. And this is all there is to it. Yeah, this is why so translating one says onto the wall with the Werner module, just gets the Werner module. But if we instead we translate out from the walls, which we can do as well, right? We could well make a similar picture. Make a similar picture, but translate out from the walls. So we have here this guy, and now we want to translate from mu to lambda this Werner module, say delta 2, start to 2. So this guy here. Yeah, I try to nicely draw the picture like this maybe. So we have to tensor this with a finite dimensional representation with an extremal weight here. So if we look like this. And so we see that among all the subquotients, there are two subquotients which have the correct central charge. So this will have a Werner flag with subquotients delta x dot lambda and delta xs dot lambda if say the isotropy group of mu under the dot action is just 1 and s, and the isotropy group of lambda is trivial. And then you can sort of write out what this translation functors do to Werner modules in general, but I won't do it because I don't need it. Hey, okay, so this is this business with the translation functors, and now that I've introduced them, let me tell in particular, yeah, that we if we are going back to this case of SL2, I mean we discussed in detail this category of 0, yeah, which would be the plus in our old notation, but 0 is sort of better. Yeah, it's an easier notation. And this will be equivalent with a translation function from 0 to, I don't know, n to O n rho for all n bigger or equal to 0. So all these other blocks, so this is in the case SL2, yeah, SL2. So you recall in case of SL2, we sort of this finishes our study of category O for SL2 essentially. Yeah, we had sort of a clear picture what would category O look like at the singular place where it's just vector spaces, or at a space where the weight is non-integral, where it would be just vector spaces times vector spaces, just all gamma modules that are useful. But these sort of integral blocks we didn't yet discuss, yeah. And they would look sort of a bit more complicated, but with these translation factors we can find okay, I will not prove it's not difficult though. But so we now so all these blocks have also 5 incomposables and they look interesting. Okay. Okay. And so let me prove some more things about these translation functions. But really not I mean I have to be a bit short on this. I mean, the first thing I should do is there are the junctions. So this translation is adjoined to this translation. Always. That's this. And I mean, this can easily be seen if you look at what we did here. Yeah, we wrote this as an injection factor, a tethering factor, and a projection factor. And now the adjoint to the projection factor is the injection factor. The adjoint to tethering is tethering with the dual module, which will exactly have the highest weight needed. And then a junction of the injection is a projection. So that's it. And then the most important thing we would need is that the translation makes projective to project. Yes. But I mean these translation factors are also clearly exact, right? Because the composition of 3 exact factors. And I guess adjoint to an exact factor now, but I don't know whether it's left or right exactly what you mean, but yes, both anyhow makes projective to projective. Yeah. And maybe I should also tell that this computes with gravity. So T under mu dual is dual T under mu. Oh, essentially for the same reason, right? Tensoring with E compatible with duality and the other things too, and so it's all quite clear. Okay. Okay. And now, now I need some sort of description of these anti-dominant of these projective objects to be able to translate it. So so what one usually does is so see now let S is simple fact. So like this, here is our simplest lecture. Here is again minus the rho. And then we define so-called wall crossing. Wall crossing. Which maps, it's called theta s. And in the following way, so let's just specialize it only to the principal block. So here we have 0. And now we choose any guy on the S wall, u. So u, and then we just define that this will be translation from 0 to u and translation back out from v to 0. And so this mu is on the S wall. So the isotropy group of mu under the dot action would be just 1 in S, shown here. And okay, I mean, it would be in this shifted integral weights. So I translate first onto the wall, and then I translate out of the wall again. And what happens with what then happens if I apply this to a Werner modulo x dot o? Well, it does. Yes. Let me just write it maybe so. Okay, here's a Werner flag with sub quotients delta x o and delta x. The important thing is always want to get smaller. So delta the same and xs dot. So if I take the Werner module looking here, I will have a delta flag with these two samples. And if I take the module sitting here, if I translate it in the wall, it will have these two subquotients. I mean, both these Werner modules is the same. Okay. Okay. And now I hope you see that okay, I have to tell something. So what would be the description of the projective covers of x dot lambda. So see now we take, say, the x is in the y group, and I have here a reduced expression, okay? S1, SR. So this is a reduced expression of x, which is in the y group. And then I would know that the projective cover of x dot O could be obtained as follows. So well, we could take the Verma module, the projective Verma module, and then apply this the sequence of projective functors in the other order. So theta S1, theta S2, and so on. Theta SR. And then we would know that this should be isomorphic to some projective object. So it will be a some of indecomposable projective. And it would be a sum of this I, where y is smaller than x. So yeah, so because all these wall crossing functors, they make projectives to projectives. And how do the Verma flags develop? Let me try to make a picture. It's just the same picture you might have seen how the Cauchy polynomials develop. So but now I really have to take the x from the right and not from the left. So if I have here I draw just delta O, and now I apply the projective functor wall crossing theta S. This is the S wall. Then it will get. Let me write just a 1 to signify that this occurs once in the Verma flag. Okay, here now it's not polynomials, unhappily enough, it's just numbers. So if I apply theta S, well, then it's a 1 here and a 1 here. And if I apply again theta P, say, okay, now I have to a bit careful with the walls. So it would get this one gets a sort of met here, so I have 1, and this one would sort of be doubled here. Yeah, they always get doubled along the sort of T wall. The T is now the reflection sort of. Well, this is the picture if I act from the right. Yeah. So it's a bit. Should I try to explain maybe? Okay. So here I make 1. And so this will be the Verma flag of theta P, theta S, dominant Verma. Let me try. Right. I should make a pause in 5 minutes. So let me try to explain you what these pictures mean. I mean, this is not difficult, but it's I think very helpful if you try to draw pictures in this way. namely, see, let's suppose we have a reflection group. To make nicer pictures, I might even take an affine reflection. Yeah, but as you wish. So let's imagine we have an affine reflection, right? So here maybe like this. Yeah, this is the mirrors of the damn thing, and this is an affine reflection. Okay, generated by all these mirrors. And now now we fix an alpha. We call it A plus. And that we know that the Y group, well, the reflection group, now the group generated by the reflection along all these mirrors, it acts simply transitively on the set of alphas. So it is bijective to the set of alphas by applying fix any alpha and map an element X to the image of the alpha. Okay, in this case, in this way, we have a bijection from this group to the set of alpha. Okay, so for example, yeah, and now now the walls of these alcoves we singled out. Let's call them they are sort of called simple reflections in this case. Well, they form a Coxeter generating system. So let's give them some names. That's S, there is R, and there is T. So this is the reflections generating the thing. And now I want to know if I take X, T. Okay? So I have the right action on reflections on this thing. Yeah, it should get mapped to the alpha of X, T, A plus. So how to see this right action in this alphabetic picture? Okay, so what I should do is say, okay, these walls of this thing, I give them names like this. And now, now if I reflect sort of these borders with the names, they get reflected too. So all these sort of walls here, yeah, so these lower dimensional faces, they get names by moving around with the reflection here. So let's suppose our alpha of XA plus is here. Then we know that the alpha of XTA plus should be here. Because the alpha of TA plus is certainly the one which meets A plus along this line. Yeah. So this is TA plus here. So if I move this domino around and the A plus lands here, then the TA plus has to land here. Yeah, in the sort of in the alcove which shares a wall of type T with yeah, and so this is what I try to draw here. Yeah, the sort of the right action. Yes, and so now this is time for a pause. And there will be pause until, let's not be too cheap with the pause. Everybody is tired. Let's make a pause until 3:30.
We're not sure it's supposed today. What? I mean, I think so. I mean, he doesn't. He just says stuff like certain push forward by certain mortars and only raises commercial degree by 1, but I can give you an example where it's like 3. This O pattern thing in XVM, this X with an O above it, and makes if you just the ordinary but it doesn't matter. So like the competition has take this false, but it doesn't matter. So if and those are want to be some. I don't have to slow down. And probably because technology can yes, sure. Yeah. If it's something out from the wall, then nobody gets that. Yeah. Then it's there. It only happens I found something inside. Yeah, if you translate one somewhere, I thought we can start with only the wall there. This is a technical under the law. Those from above, you know, sometimes the young and onto the wall again. This is just multiplication by a because the element of the basis of the yes. So that's the two halves of everything. It just sit down there. If you get out, so this is sort of from grocery. So this is now is new on so this is This is so then I this is the thing that not conservative, and this thing is actually conservative.
Not
This is not conservative, and this is that's why I think I go out from the ball and into the ball. So this is conservative. This is not offensive. This is positive.
No, l'ho sentita la settimana scorsa, infatti stava pensando che forse l'idea di non voler fare il postdoc, no, queste
Non era buono, era
no, era di fuori, era
Yeah, exactly. Yeah.
quindi sarebbe stato sì.
sì, puoi chiedere l'affidamento però non completare
So the formulating.
Yeah.
no, ma si aveva anche degli illustrati perché c'è una forma, lì posso fare la differenza, e c'è per la differenza.
If that's translate inside, it's always the term.
Yeah, the whole it's not only kind of that special banking in the law, I think that's the big one and the kill something. That's the only thing that happens.
Yes, live to me. Engine.
Yeah, good. Smash. Yeah, zero. Okay, thank you.
Yeah.
Quello che c'è la gente che può parlare, si viene deve veramente essere la differenza se lui va normale, perché è veramente superiore. Però se la gente si fa fare lezioni, non c'è da spettacolo, perché in cosa puoi fare? Cioè, non è che devi andare come puoi imparare, secondo me se tu puoi imparare che lei sia brillante in qualche modo la voglio mettere in pratica. Devi dice che è però mi spiego un po' l'effetto però prima di cioè devo imparare ma che però lei insegna zero anche sì però no, ma gli altri
One as a serious question. Or maybe I think there's a whole community to answer my question. I thought I buy shoes. I don't have good shoes anymore. Or they are not sort of up to Italian stuff. Yeah, but if you look at them like this, no. Yeah, absolutely, Philip. So what's the serious place here?
You want like fancy things or normal things or
I don't want tennis.
no?
Just sort of reasonable level.
I never bought shoes there, but I think one place where some people go is at the beginning of Piazza Barella. We have a map. Piazza Barella, so but so they have leather shoes and it's not cheap, I think, but
Yeah, but it's not reasonable. I mean, leather shoes are never really cheap.
no maps.
Is that already? Okay.
Yes.
Yeah. Okay.
Okay.
It goes onto the San Lorenzo.
So you know this street?
I think
This one, the Altinante, I don't know.
yeah, I think so. This is where the Altinate gate, right?
Yes, exactly.
Yeah.
Okay, so when you are,
Now you need to first go to Google Maps and then go.
Happy with the location.
okay, no, but, so,
We just found out so.
yeah, okay, so, so Altinante is here,
Yeah,
so you prove the Altinante,
yeah.
and just before reaching the gate, there is this side street.
Yeah, okay.
And essentially at the corner or shortly after the corner, there is a shoe shop.
Okay.
It's called Logo Calzature. In fact, there are three shoe shops here. One is more like Birkenstock and stuff, and this one is more like traditional. Yeah, it's I think they have.
Very. Thanks.
That would be, I don't know. And there used to be another one in the same street, but it closed. Yes, there is. You can go there. Yeah. Yes.
I think this.
But in any case, at least you have a nice walk. And then you have lessons there. And there's I think also no. Maybe too deep, so
Yes. I was saying,
They don't pay very enough.
yeah, I guess so. Because I think yes, I think also in this street but yeah, but probably I would just go here and see what they have. Okay.
Almost have to walk.
Everyone's in the standing streets. Yeah.
You should probably find this.
Unless you just want to go in mountain. So what you
Yeah. So I try to explain how it works. And for example, this thing here, we would know that it has a Werner composition factor here, and all the other Werner composition factors would be smaller in the Breuer order. So it need not be a decomposable mode. But here it is, but in general, we don't know what that is. This is sort of a nasty problem, but what we know is so that this whole thing has one direct summand like this, and then other direct summands we already know better. Partly Schmidt decompose. Okay. And now let me tell you something which I will not move. Namely, there is an isomorphism belief. So that if I go from category O0 to itself with all property because S, and then I go down to C modules with this control B, then there is a functor here which makes the diagonal commute, and the functor is restrict scalars to the invariants inside the co-invariants, and then go up again. Okay. In fact, CS is the cohomology ring of a partial plate variety. Where C is the cohomology of the big plate variety. This is sort of a minimal parabolic sitting above B person. Okay. So if you believe this, then you have you can put a V here, right, to this description, and you find that V E x dot 0 plus some smaller V y of 0, but y is smaller than x. This will be isomorphic to C tensor CS1, C tensor CSR, C tensor, and so on, CS1 C tensor, well, you have to take the value here, which is just the one-dimensional object. So we see that we should take this C module, finite dimensional module over this finite dimensional ring C, and we should Schmidt decompose. And then there has to be one direct summon, which we don't know already from Schmidt decomposing for smaller expressions. And this new direct sum, this was the diagonal control. And this is not a very explicit description, but at least it isn't. Okay. So this is our description of this guy, which we call dx, the special indecomposable special parameter. And now let me explain why it's also the intersection cohomology of whatever. So there is a very more or less the same description for the intersection cohomology. Namely, we know if we would want to describe the intersection cohomology as a module over the whole cohomology ring, yeah? How would we do this? we would maybe do the following thing. We would take the IC complex of the 1-point cell, which is sort of, well, I thought ICE. So this is a skyscraper sitting on the 1-point cell. And then we would push it down to a partial flat variety and pull it back up again. And here we have sort of G mod B, which projects under TS state to 3 modulo S. So we push it down and we pull it up again. And then we get the IC complex for S. So this would be the IC complex for S, I think, which is probably this one. I recall correctly, maybe it was -2. No, it wasn't minus. It was a -1, I think. And then we keep going. We push down and pull up. And then we will get something fairly simple, where there's IC X may be shifted by minus length of X. Is one summit. And then the other summits are some IC complexes IC Y, where Y is smaller than X in the real. I mean, you see this is by a decomposition theorem. Right? I mean, if we do all these operations, we never leave the category of complexes of G's where here maybe some high, some shifts. We never leave the category of semi-simple complexes. Perversely semi-simple complexes smooth along the Breuer stratification. Yeah, so this category say derive smooth along the Breuer stratification on B of B. This always gets into itself if we push down and put up again. And also if we take it semi-simple objects, yeah, so perversely semi-simple objects, or how you call it. It always gets back to itself. And so what comes out of this process has to be something of this type. In fact, it's also another way to say, in fact, it would be this is a T, and this is a lower storm. Now we are definitely. And I mean, you could also say that if you want to put it in one stretch, it would be take the constant sheaf of the Boltzmann resolution and push it all the way down. It would be sort of a one stretch description of it. And now, okay, now we should have a similar picture here. That if we take, say this derived category, and now I don't, let me be careful, at least if I take the simple objects, and I go down and go up, and I go to the same thing. Or here I take hypercohomology, and I go 3 T modules. Here same. 3 modules. then again, I mean, here it's integrated, whatever. Then again, I get a computing diagram. If here I take extending scalars over C S. And I should probably make a shift. Maybe not. Okay, this I didn't now think through. I mean, but I don't think that it should go. Okay. And so, okay. Mm, And so I have now to argue a little bit why this decomposition here, if I apply H, should be the same as this decomposition here. I mean, why if I apply H, it would be also a Schmidt decomposition into decomposers. Okay, and there is some argument to do, and in fact the important information is that this hypercohomology will be fully faithful on these objects. And this is sort of a non-trivial thing. Yeah, also, I mean, so I claim that in addition, so I claim that maybe in addition that H is fully faithful on this derived category here. So semi-simple objects. And for it to be fully faithful, I should go down to C modules, which are now separated. And how to prove that this is fully faithful? I mean, okay. I mean, there is sort of a direct geometric proof, but this is complicated. I mean, to prove this geometrically is quite tricky business. But you could argue that it's faithful, and then to count dimensions. You know what is the dimension of homomorphisms between such objects, because it's like homomorphisms between these projective modules, and they are given by the Werner flag, and you know it all. And then you can count dimensions and find that this has to be fully faithful as well. And if you want to do it geometrically directly, okay, I mean, Ginsburg wrote out an argument this way. I will reuse it sometime, but it's sort of complicated. Okay, but if you take all of this together, you find that. Oh, let me get out of it. you find that this V X 0 isomorphic to the X size C complexes. And this gives us a proof of the Cauchy convection. Because these intersection cohomology complexes know sufficiently well. We know, in fact, how this decomposition works combinatorially. Okay. But now, in fact, we can deduce even much more funny things from this isomorphism, and this is what the conjecture of Davidson and Ginsburg, and so let's let me explain. I will skip off. Yeah. Because now the very funny thing is that we can feed the theory sort of to itself. Namely, finally, we know that the permanent sheaths on move around the orbit of V naught B. This is equivalent to the category O0. Yeah, this is sort of by localization and some tricks. So this is based on Bernstein localization. I think I mentioned it, and then Riemann-Hilbert correspondence. And tricks, which I didn't explain so much in passing. Well, yes, I did. Someone want to know. Okay, so we have such an equivalence, and in fact, here the simple representation X dot 0, it will correspond to the intersection cohomology complex of the set B X. Wait. Not I said something wrong. It will be the intersection cohomology complex of the cell B X, longest element of the Y group B or B. So W and B is long. Right. For example, if we have the trivial representation, the trivial one-dimensional representation should be under localization. I need a D module whose global sections are just the ground field. Now this D module is regular functions on the whole Flat variety. They are a D module, and its global sections is just a ground field. So this is it. So the D module will be regular functions on the whole Flat variety. Yeah, it's a kind of strange. Yeah, there is this very big object which corresponds to this very small object. and this corresponds to the constant perverse sheaf. The perverse sheaf, which is just a constant sheaf on the whole flag variety, but put in some nasty degree. Yeah. Minus real, minus complex dimension. So it will be the intersection complex of the big cell. Yeah.
So this is this intersection complex the intermediate extension of the constant sheaf on this cell?
Yes.
Okay.
Yes. I should make a bow. Okay. Yeah. 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 And on the other hand, if we have here the simple Wörmer module, yeah, it's simple Wörmer module is highest weight minus 2 rho. It will correspond to take as a D module a sort of a skyscraper D module sitting just at one point. Yeah, if you have the D module sitting just at one point, this is sort of the D module generated by the Dirac delta distribution sitting at this point, and all its derivatives. Yeah, and so this looks like a Wörmer module. Yeah, it's the global section. There is no draft, just global section. It just sits at the point. This would be the Wörmer module, and so this is correspondence, and in fact, this will pass to this will be fully faithful even on the derived setting. So the x say no, I mean the x between the two IC complexes. Let's give some name. Let's call it x. Maybe it's too late to change notation. So x w IC yw will go bijectively also to the x I in category O of the Lx of O L1. No? Oh.
This is text on the left.
On the left, it's sort of morphisms in the derived category. And here I put a shift. Okay. So it's not accurate at the moment. It's just sort of morphisms in the derived category. Yeah.
Yeah, I was just wondering different font than the one on the right.
What?
Because I was wondering because there was a different font than the one on the right. Because I think this morphism in the right category, they will be like morph to the X for these two sheets.
It's true.
Yeah.
It's true.
Okay.
It's true. It's the same as X for perverse sheet. This. Yes, absolutely. And so what we find is so I try to explain that this is I try to explain that this goes isomorphically to the homomorphisms of C modules from this XW to this VYW, yeah, these special modules. And these are also isomorphic to homomorphisms of the projective cover of XW dot O YW dot O. Okay, so so what do we find? What do we find at the end if we sort of put all this together? We find a very strange thing. Namely, let's get a fact at the general theory. Yeah, I mean, the general theory was that if we consider the algebra, the category O, say O0, would be equivalent to right modules of an algebra A, finite length, where A is the endomorphism ring of the diagonal sum of these projective parts. Yeah, x dot zero. X transitive value. This is sort of by general, just for every more or less an arbitrary leading category of object, finite length and projective, we have such thing. But now we see that this is also isomorphic to the algebra of X of the simplest. But we should add some other things. So standard sum. Simple of X. X doesn't use something. So just long element bias. Right? Because these because these the homomorphisms between these projective objects are the same as the homomorphisms between Racine complexes, are the same as extensions between simple objects. So we could put it in another way. We could say, okay, I mean, under this equivalence, let's call this algebra now A, okay? Because this is a grading algebra. And under this equivalence, I mean, the sum of simple objects, x dot 0, has to correspond to the sum of simple objects, which is just a 0 with respect to this grading here, yeah? Which I would consider as a modulo everything bigger of degree bigger. So what we find is that A is isomorphic to X from I0 to sum. Right? So there's a quite funny, quite funny, yeah.
When you use direct sum as x times target, or what's that?
What?
You know that in your direct sum on the second line, you I x times 0 should it?
Yeah. Yeah. I mean, I have to be absolutely right. I mean, there's an isomorphism, but the idempotent 1x goes to the idempotent 1x value. This is this. Now, there were sort of not so many people going to this talk on causality yesterday, but in this formalism, we deduce that this is a causal ring, which is isomorphic to its own causal union. So A isomorphic to A union, which is sort of extremely standard. Usually, the double dual should be the the same ring, but here it's just its own jewel on the nose. And this is kind of from my point of view, this is kind of a bad accident. Yeah, I mean this is not canonically true. This is not canonically true. So let me try to massage the whole argument to see why it should have to do something with Kosovo with the Schlangenhanswort. Yeah. We are.
Can I ask you a question?
Yes.
On this board, like on the top board,
Yeah.
it depends on I, and on the bottom board you have no I. So do you mean that like the bottom board is like the sum over of I, or?
You mean here?
Yes.
Yes.
Here you have just an on. And
Yes.
Okay.
So here it's just all homomorphisms of C modules. But here, I should take here sort of a sum over all i's.
Because for a fixed I, it's going to be the homomorphism that are like graded up to be I, right?
Yeah.
Okay.
Yeah.
Absolutely. Let me forget the grading.
Yeah. Yeah. Thanks. Okay. So now let's see what where the Langlands duality is. And for this, let's discuss in more detail what this what is this cohomology ring of the background? Well, say one way to describe it. I mean there's I don't know which way you prefer. But at least an easy way to describe it is the following. You say you make a map from the characters of the maximal torus. And you map it here. And in the following way, if you have such a character, then you can associate to it an alignment. You say, oh, lambda will be alignment here. I mean, I could write it G times C lambda over B or something like this. Yeah. Which will be the line bundle over here. And this is a second Chern class. Well, Chern. D1. And this will be in H2 here. Yeah, so every integral character here gets an H2. And then we have to check that this map, so this is a map, in fact, to H2, and then this map induces a map from the symmetric algebra of all these guys, yeah, of say X of P tensor sleeves. Of this is to make and this is to be put in these two blocks. This then gets mapped to homology rate. And this thing is essentially H dual. Yeah, so it's a symmetric algebra of H dual, which gets then mapped here and gets sort of mapped to this C of H dual, and which solves then isomorphism. Yeah, this is essentially. And now if you recall what happened on the other side, our C, our C was in fact a quotient of the center. And the center lies in, well, gets mapped to S of H. Symmetric algebra of H, not of H dual. Mapped in symmetric algebra of H, and then there the graph invariance and so on. So just to say that in fact on both sides, on one side we have H dual, and on the other hand side we have XH. So we, yeah.
Sorry,
Question.
maybe I just have limitations. What's C of H dual?
Well, C of H dual would be
That makes C.
So C of H dual would be the symmetric algebra of H dual divided by the things of positive degree, which are invariant under the Lie group, and then the ideal generators. And here we had the same thing without the dual on the other side. So to get sort of a really to get a really canonical identification here, I should take the Langlands dual on one side. This is a shut up, yeah, because then we get the dual torus. So what we would really have is, yeah, so in a way, all along, we should have taken dual C. Yeah, and then the whole thing would be much more natural. Okay. And now I don't know. Now you can jazz up. You can jazz up this story in different ways. And I think I will stop and stop that one. Question. Well, I mean, it's extremely weird. It's definitely extremely weird, and it's and in fact, I should tell that sort of how maybe this is something I can tell. How did Basil and Ginsburg cook up such weird thing? I mean, and okay, the thing was the following. They realized this was sort of generally known that that this matrix of Cauchy-Lucid polynomials is inverse to, you take the same matrix, but you add the longest element, and then you transpose it, and then you put some facts. And then this, so the inverse matrix to the matrix of Cauchy-Lucid polynomials, this is again the matrix of Cauchy-Lucid polynomials. So This was already due to Kashan and Yusto. And they try to categorize this business. And in general, there was also this quadratic algebras and causal algebras were sort of at the same time. And there you know that if you have a causal algebra and take its causal dual, then the Poincaré polynomials of these two are inverse to one another, up to transposition and so on. Basically, it's very easy. And I said, okay, if these matrices are inverse transposed to one another, maybe this algebra is just causal dual to itself. This was how it came about.